Okay, hello. I'm Jonas Horreis, penetration tester at dissecto, and today I want to talk about automotive Ethernet penetration testing or /Ethernet penetration testing with Scapy, especially how we use Scapy to test automotive Ethernet or Ethernet, and also a few lines of codes what you can do, maybe even in front of a penetration test, so the ECU doesn't break in half an hour of testing. So, we used this slide last ScapyCon. We are still actively improving Scapy to support everything automotive specific. The big advantage of Scapy, since it's over 20 years old, is Scapy was initially written for Ethernet. And now the automotive industry goes also in a direction of Ethernet, automotive Ethernet. One big advantage of this is we can use everything that has been implemented for Ethernet, all packets, all attacks, like the NDP attacks presented in the keynote. They are all available in Scapy, and we can also just use them in the automotive domains, if NDP is implemented, of course. There are still the same recent changes as last time, because they are still in work. DoIP, SAM-IP, AutoSarpedios, everything just got a few bug fixes to make it more fluent with, let's say, different implementations of these protocols. And now I want to talk about a few things we do. So first up, Ethernet versus automotive Ethernet. Ethernet has more cables, so 4 or 8. Automotive Ethernet is only a twisted pair. But what's really the difference in testing it? Well, turns out there's not a lot. The only concern here from a testing point of view is how do I connect to my device that I want to test from, or to my DOT. For Ethernet or for OBD2, we can use an Ethernet cable, or if in case we need to connect to the individual pins of the car, for example, we can just cut the Ethernet cable and take the 4 cables we need. For automotive Ethernet, to connect it to a PC, we need an adapter. There are basically 2 possibilities of how to do that. We can use a USB to automotive Ethernet stick, which directly fits in the USB port of a PC, and when the twisted pair comes out on the other side. One example is our developed Hydrolink. The other possibility would be to use a media converter, so it's an external box. Automotive Ethernet goes in, Ethernet comes out, and then we can connect to our PC. For the operating system, so I'm using here Linux here, but same for Windows and most other operating systems, there's not a seeable difference between Ethernet or automotive Ethernet. So once I connect it, I'm physically connected, it will just, in this case in Linux, pop up as Ethernet 1. So the operating system just connects Ethernet and is done with it. This has a great advantage. We don't need to care if we're using Scapy or other tools like Nmap, TestSSL, and so on, if we are connected to automotive or non-automotive. The only thing we need to make sure is that our adapter or media converter uses the right speed and is also configured correctly. Automotive Ethernet uses master-slave, so we need to have the opposite of what the ECU does. Once we are connected, we can start testing. Here, a quick, very generalized overview of how Ethernet in the car works. So with the change to Ethernet in the car, there's also the change to we get more and more high-performance ECUs or domain controllers, or however you call them. So basically, we have very powerful ECUs in the car that are responsible for, they get the data from other ECUs and then calculate something with it, like the ADAS system, the cameras, or the infotainment. And the general flow of data is from the data collecting ECUs to the high performance ECUs. So the camera data gets fed to the high performance ECU since it needs to do something with it. And that leads to here the first common issue. It's basically the first test we do if we get an ECU. It's flooding. In the world of CAN, we have a data speed up to 10 megabits, and the topology is that every ECU is on the same bus. Which means if ECU gets a software update, all the other ECUs also get basically the full load on the bus, because the ECU is getting a software update at preferably maximum speed. Which means ECUs are tested against high or even maximum bus load, so flooding over CAN is rare. In the Ethernet world, we don't have a bus. We have a point-to-point communication. So if we want to update a ECU, mainly only the gateway gets our packages, and then the gateway will route it to the right ECU. And the other ECUs will not see the software update. Which means if the ECUs will not normally, under normal operating conditions, never come close to the 100% load of Ethernet. Especially if we have a data collecting ECU here, it likely will send a lot of data. Let's say it's a video camera ECU. It will send the data to a high performance ECU, but the high performance ECU will not send a lot of data back. So it has maybe some settings it needs to change or some operating variables it can send, but it will not send the whole video stream back. And additionally, Ethernet is a lot faster, which is good if we want to send a lot of data, but it also leads to the problem that we can send a lot of data. Meaning, yeah, these are our favorite two Scapy lines for the first test. It's just make a lot of packages and then send them. Scapy has, maybe you see here, it's not a standard send function here. Scapy has a send pfast function. I mean, we all like Python. Python is our favorite language, but one problem is it's not the best optimized language to craft a lot of packages and then also send them real-time out. So there's the send pfast function, and it basically will build all the packages, write them into a file, and then use TCP replay to actually send them. So we exit Python to just send a little bit faster, just a little bit. Yeah, these the reasons I said before lead to the consequence that ECUs that are not tested against receiving a high volume of data are basically much more vulnerable against crashing if you send high volumes of data, because, well, they're often not tested against that use case. Next up, let's go to the evolution of the higher level protocols, especially in that case diagnostics, UDS versus diagnosis over IP. On the top, we see the legacy version of sending a UDS package. It's just CAN or CANFD, doesn't really matter, then ISOTP layer and then UDS. So yeah, we just send a message and then we go back and receiving the answer of the ECU. If we want to do the same over Ethernet, it gets a little bit more complicated. We have more layers in Ethernet. So we start at the Ethernet layer, then we have VLANs, then we have IPv4 or IPv6 or both. Then we have TCP and UDP. For DoIP, we actually have both, so TCP and UDP. Then we have DoIP, and after that, our UDS part comes. Now, this is not a single message. It's actually, there are actually more that needs to be done before we can send a UDS message. For example, we need multiple handshakes. like if ARP is implemented, depending on the ECU, we first need to find out which MAC address the ECU have, when we need to do a TCP handshake, when over IP we first need to do a routing activation before we can send anything. So this leads to A, we have more layers, and B, we have more complicated layers. So these layers have more implemented function than ISOTP and CAN. So I'm starting in the middle here, larger stack, more complexity. We have more protocols that are implemented, and therefore we have more code base and more code. I know we are all excellent coders, but normally more lines of code means also more errors. And therefore there's just a higher possibility of having errors in the more complex stuff. One point is also a maturity gap. CAN is quite old. I mean, yeah, Ethernet is also old, but not in the automotive world. And therefore, we have a lot of CAN stacks that have been tested, refined, like we are not programming every CAN stack from scratch. If we have a new ECU, we take what's there, and that is there is already been tested. There were bugs in the past, but they have been fixed, and therefore the CAN stack in general is already very tested and has not that much issues. For the Automotive Ethernet stacks, they are relatively new and they are still evolving. So we see additions, like for example, TLS is a new addition, and then this and that. Therefore, they are still in development and they are way less tested just from a time perspective. And there's also the error potential. We have a lot more features on the individual stacks. Also comes with a larger stack, more complexity. And these features also introduce a broader attack surface. For example, with CAN, we have normally don't use dynamic ID resolution. We just use a certain CAN message ID for that. ECU can have multiple IP addresses. You can use DHCP to get more IP addresses, and yeah, just all the functionality combined leads to more possibility for making errors. Now, this stack is nice, but many of you will know this is the old picture of DoIP and UDS. We now have a new standard with TLS. And it gets to that. So we still use the first part of the message we had unsecured without TLS. So this is the standardized way. So we first communicate unencrypted when the ECU tells us, please change to encryption channel. So we close the whole connection we did, and then make a different connection at a different port, and then use TLS. This leads to even more overhead because we need to do the TCP handshake again, the TLS handshake, and then DoIP again. And now sorry, the next slide will be a bit scary. There are numbers on there. Just for how much overhead is it really? I mean, we have 3 layers at the CAN-FD, then we had 5 layers at unencrypted, and now, well, we have 7 layers. Oh no, we already had 6 layers here, but you don't send UDS unencrypted. How do the bytes change that are on the cable? It looks like this. So on CAN, we have 14 bytes on the cable. It's just one message, and we have a UDS message. 14 bytes. I know CAN only has 8 data payload, but we also have identifier, we have CSC, and so on. For CAN-FD, we have 70 bytes, so roughly, it depends on configuration. But we basically have the same overhead as CAN, so we can send a lot of UDS bytes. Now let's take the case we want just to send 2 UDS bytes. For Ethernet, we need 672. So 670 bytes overhead just to speak unencrypted, no security to the ECU. Why? We need to do a TCP handshake. Sometimes we need to do ARP. We need to do DoIP. And after that, we can send our UDS message. And so we actually took the bytes from a real ECU communication that's taken place. And if we now want to change to TLS, that was a quite convenient thing. It's actually times 10 the complexity in case of what's on the cable. So basically we need to do the handshakes times 2 most often, and basically every plus you see here is a single message. So just the amount of messages on CAN, we can do everything one shot, one message. It leads to just for the TLS stack times 10 without TLS. So we can test the single layers over everything that was already implemented in Scapy, Ethernet layer, ARP, DHCP, and so on. But now let's say we want to actually test UDS. It's quite inconvenient to do all the back and forth handshakes and so on. Luckily, there's the DOIP socket or the UDS DOIP socket in case you want to do DOIP, which does it for us. So here's 2 examples, one time without TLS and one time with TLS. It's actually the same socket, just either socket will even automatically detect. So if the ECU is not happy with unencrypted communication, it will tell us in the DOIP return of the routing activation. And the socket automatically detects that and then switches to TLS port if the ECU just wants to speak TLS. So the main Python overhead here is just getting the SSL context right, so we can connect to the ECU. It's just the same socket we can use here. And basically after that we can speak encrypted with the ECU without even us needing to do anything. We can just send UDS here and receive a response. Also the UDS DOIP socket, if we go a bit back to what's implemented, can be used for all scanners that use DOIP. So we can use just every UDS scanner that's implemented in Scapy. We can use the same functions we use for CAN, like just for Ethernet, just we exchange the socket. So now we have how we can test. So what can we actually test for? And one very common Ethernet issue is we have TLS and we have UDS. Who's responsible for what? So if we look at the security goals we can achieve with UDS and TLS, they are the same. So we have UDS functions that can prove authenticity, they can prove integrity, that can prove confidentiality, but it's the same for TLS. So before using UDS and TLS together, first the boundaries of what protocol does what must be clearly defined. For example, if we see a TLS implementation with deactivated encryption, deactivated authentication, why are we using TLS? Therefore, it's important to check if these goals can be achieved with the implementation. So if TLS does nothing, does UDS do the part? If UDS does nothing, does TLS do the parts? And these unclear definitions lead to some issues in the field. For example, if I guess the UDS stack thinks that TLS does the security and therefore on UDS side you can do everything, and when TLS does nothing, then you have free access to the ECU. So one additional thing we can do over Ethernet is using the Scapy automatons to make our own servers. So in this case here we have a HTTP server which was used for software updating. And with the automatons in Scapy we can just emulate a software update server and then see how the ECU reacts if we send malicious files which we somehow malformed, or even wrong answers which he probably is not expecting in the car. Same for SumIP. So we also heard an introduction about SumIP in one of the last talks. We can also do it in Scapy by creating SumIP answering server and simulate basically ECU, and then use this server to just change a little bit of the messages to see how the ECU reacts if it gets malformed messages. And the attack surface here, we already heard the attack surface of SumIP. I want to mention there are more attack surfaces in our experiences even, are the proprietary SumIP protocols. So many OEMs use SumIP, and they really like SumIP, so they use SumIP for everything. They use SumIP to transmit CAN frames, they use SumIP to transmit ISOTP frames over Ethernet, they use SumIP for over the update, they use SumIP for the whole SecOC key exchange and timing and so on. And therefore these proprietary protocols can lead to errors. One example I have is from the now it's 2024 Pawn to Own challenge from a Tesla. And basically what happened, they had an already known bug in the connectivity card and managed to get onto the infotainment system. But now the problem, the infotainment system is not connected to CAN. How do we get CAN messages out of the infotainment system? The solution was we can just send, so in that case, a UDP message to the gateway containing a CAN message, and the gateway would just cut off the Ethernet part and send it over CAN. So with that proprietary protocols, there's room for error, especially in the firewalling of the gateway if there's a protocol implemented. So there are some use cases to send CAN packages over Ethernet, I guess, but then you need to be really careful how does the gateway handle these packages, because if it just takes every CAN package it gets and then sends them, then basically the whole firewall is gone. Yeah, another topic is the topic of SecOC. So we also heard like we can protect messages now. So every message, not just our UDS over TLS. We can protect SumIP, AutoSAR PDUs, or on CAN we can authenticate our messages, say that everything is intact. Perfect. 1 second. Hey. And it's basically the same as the SecOC standard. It's a standard, it was written, it looks nice, and when you get into the real world and realize, okay, they just put a lot of addendums onto the standard, they do their own stuff, everyone is doing something else, and it's basically the same for SecOC. So in an ideal world, we have clear definitions, we have the 3 predefined profiles, we have a well-defined freshness value and a well-defined exchange of these values. And when the real world hits, we have an unclear generation of what is even secured. For example, if we have a CAN message, is the CAN ID part of the PDU which is secured? Or can we change the CAN ID and send the same message? What about the PDU ID? How is it generated? Or where is the list of that? Is the length field in the PDU? Or is it just really only the data? Is padding used? Sometimes padding is used, sometimes not. It makes a big difference if you calculate the MAC. Also, freshness values, where do they come from? How are they defined? We saw a lot of proprietary stuff done here. Sometimes there's no rollover handling. What happens if a freshness value is gone? Also, what about key exchanges? There are a lot of different key exchange methods out there. Also, theoretically, we have 3 defined crypto profiles in the standard. I actually never saw one of them. So in the field, you have always different key lengths, so you trunctuate here the keys, the lengths are very different, the freshness value is different, the trip count is different, and so on. So this is a huge issue in implementing it in Scapy. And therefore, now in Scapy there are SecOC for CanFD and also AutoSAR PDUs, but basically they need a bit of change to work for everything. So these are the three main functions. So here we have what payload do we actually want to make. Then how do we get the key and how do we get the freshness value. And these are in Scapy, but they often need to be altered depending on what the ECU uses. So here, for example, in this case, we take the data ID and the payload. How do we get the data ID? We take the identifier. Is this the case? Well, depends on who manufactured the ECU. Yeah, so another thing is the UDS authentication service. So nowadays we gone away from UDS security access. Instead, we go to UDS authentication service. The authentication service now works like this. You first need to connect to an OEM backend. You need to get a diagnostic certificate, which will include the role you are allowed to do. So, for example, an engineer gets more permissions than just a normal repair shop tester. When we send that certificate to the ECU will generate a challenge, and then we need to forward the challenge to the server because the OEM backend actually solves the challenge for us. And then we can give that proof to the ECU, and the ECU will unlock the functions depending on the certificate we gave it to it. So if we think about the UDS security access, it was just we get a seed, we calculate something, we send it back. Now we have certificate exchange before that. And yeah, here's an example code how to do it in Scapy. So one function is missing here. So first we need somehow to get the certificate. We need to write a function for that. Hopefully there's an API from OEM. When we send it to the ECU, when we get our answer, and when we send the challenge here to the backend, and then we can send the authentication to the ECU and hopefully get authentication success. So now to test, we can change everything here. And one thing that we can try out a lot is how does the certificate parsing work? And if you have a certificate parser, certificate parsers are relatively complex in that they have a lot of fields they need to check for different values. We have multiple times in there that can be checked, and there can be a lot of issues with that. For example, buffer overflows, memory leaks, integer overflows, and so on. But also certificate validation issues. For example, you should never use a certificate if the signature is not correct. So yeah, something like that. Or even this is the standardized procedure. What happens if you send proof of ownership first? How does the ECU react to that? Additional thing is how does the proof of ownership work? How does the challenge of the ECU work? So in the past, random generators or in automotive systems have already been attacked. Here's an example from CMOS boot. So was Siemens bootloader from Conti, ex-Conti. And basically, if you have a weak random generation, your follow-up encryption can be significantly reduced or even broken, because basically we can pre-calculate the keys, and therefore we can get the security authentication without even owning the key. One thing you need to do here is analyze the randomness. We use the NIST statistical suite for that, so we just use Scapy to collect lots and lots of seeds from the ECU, and then we give it to the NIST statistical suite to tell us how random these numbers are. yeah, so this is the bottom part here. The upper part is we can send a lot of certificates with Scapy. The main part is generating that. For that, we can use another open source tool here, in the example Frankenzert. We make tens of thousands of certificates, and then we send them to the ECU and see if anything breaks. So one thing here, what can happen is if we use TLS or certificates nowadays, keys and everything else, we now have HSMs in the ECUs, and the HSMs can take functions of the main CPU. For example, cert storage, key storage, functions for cert handling. The randomness can come from the HSM. And then one thing here, if you test over the network, for example, you send 10,000 of certificates, you also test the HSM. If you break the HSM, the ECU most of the time is non-recoverable, because now you have locked JTAG, can't debug, and you just locked yourself out because you can't debug over Ethernet. So this can also be an issue in case of crashes. Another crashing issue, for example, if you use flooding, or there are a lot of attacks that can lead the ECU to crash. But for safety reasons, some ECU have a crash counter. And if that crash counter is exceeded, they say, okay, I'm broken, I turn off my main functionality, I need to be exchanged. And if you can trigger this over, for example, a flooding attack, you can persistently destroy a ECU because he thinks he's broken. So basically, it's important nowadays to have recover functions in case an attack happens, since even a penetration test can't find 100% of the vulnerabilities, so you likely will have one crash left, or one option which leads the ECU to crash. So yeah. Some recovering mechanism is very important. Yeah, this was it from my side. Thank you for your attention.
Thank you. Thank you. Once again, thank you very much, Jonas. Now it works. Okay, perfect. Thank you very much, Jonas. So, questions from the audience?
How do you test certificate parsing if you don't have a CA with which you can sign? Do you just use Frankenzert?
While testing certificate parsing, if we have the ability to get real certificates, we first test the real certificates, but the real certificates are tested because they work. So our main goal is to test what happens if a certificate is malformed.
Okay, so it's mostly the let's say the DAR layer, so what comes underneath the actual X509.
Yeah. So also, like if we have a CR that can sign, but I think we didn't have one yet, we could try to make wrong certificates. But then again, if it's signed correctly, then technically the ECU needs to accept it because, well, it's correct from a correct source.
More questions? Okay, that's good, because then we can go to lunch a little bit earlier. Thank you again, Jonas, and then enjoy a lunch break, and we continue here at 2 o'clock.